So last time we took a look at this neat animation of a marble rolling around in a bowl. We got these really cool patterns where it's basically tracing out everywhere except this center region. I want to get a little bit more in-depth look into this, so we're going to port this over to a Jupyter notebook. So let's copy the whole thing and then paste it into here. Paste, where's paste? Paste, edit, paste. I wonder why paste was not on the, okay, just Control V, fine. The clipboard functions in Google Colab, they don't always do what you think they're going to do. So to convert this over to something that'll run in a Google Colab, I need to take out the GlowScript reference because sadly VPython does not work in Colab. We'll get rid of marble and bowl here, because those are just visuals, right? All the math is being carried out by these items. I can get rid of that comment there. I can get rid of that there. Let's just go ahead and remove everything that we don't need from the VPython setup. Okay, great. And so now I've got a code that will run and do the math for me, but I need to record all these values that I'm interested in. And actually, I don't need the X, Y, and Z just yet. I think I'll just make a list that has those in a minute. So let's make a theta list, and let's make a theta dot list, and a phi list, and a phi dot list. There we go. I suppose I want a time list as well. So we'll do that. So I can leave all the rest of this set up, and then I can just record the information that I want into my list. So let's copy those, delete that space. I don't really need it there. Then we'll say we're going to update the lists. There we go. Let's see, I just wanted to copy my names over. So let's say dot append. Let's copy and paste the dot append so I don't have to worry about misspelling append. Paste, paste, paste. There we go. So for time list, I'm going to append T. For theta list, I'm going to append theta. Theta dot list is going to get theta dot. Phi list is going to get phi. Phi dot list is going to get phi dot. There we go. So if I run this, that should give me all of the lists that I need. So let's do a print done with simulation. Uh-oh, I ran into a problem. Oh, right. I don't have baked in sines and cosines, so I need to do, let's see, we'll do import numpy as in P. And so, you know what, let's do it this way. Since I already have these written up, from numpy, import sine and cosine. How about that? Are there any other functions I need? I think these are the only ones I have. There we go. There we go. Runtime warning, overflow encountered and double scalars. Invalid value encountered. Oh, I wonder if I was hitting the, an infinity there. Uh-oh. Maybe we better turn these down a little bit, Brian. Yeah, let's say we turn phi dot, you know what, yeah, let's start with a simple case. Let's start with phi dot equals 0, theta dot equals 0. There we go. Okay, yeah, I must have gone past the point of no return there. VPython is surprisingly forgiving when it comes to dividing by 0 sometimes, probably because it's written by physicists for physicists. All right, so let's take a look at some of our some of our results here. So we're gonna import matplotlib.pyplot as plt. We're going to make a graph. Let's do a simple graph of, let's say, theta and then phi versus time. So let's do plt.plot t list, comma, theta list. T list is not, oh, I did spell it out, time list. There we go. Whoa, there we go. That is looking pretty amazing. Let's zoom in on part of that, I think. Let's try zooming in on, let's go plt.xlim. Let's just go for the first maybe 100 seconds. There we go. That's better. So it's pretty sinusoidal at the beginning. I'm a little worried about how it decreases there. So let's see what happens now to the phi dot, or to the phi, excuse me. Theta list and phi list. And then we'll need to give these folks labels. Oh, look at that. They do have the same. Yeah, they should have the same period there because they are oscillating back and forth like that. So let's give these folks a label of, let's call this one theta. This one a label of phi. And then I believe I need to do plt.legend. My plots are legendary. Thank you very much. Yeah, so I'm wondering if we are running into some error creeping in there, because if we let this go farther... oh, okay. It looks like the theta amplitude decreases, the phi amplitude increases. That's really interesting. Let's have this go from... When does this really start to set in? Let's maybe zoom in for half of this graph. Yeah, this you can see what's happening to the envelope, but the graph itself is a little bit obnoxious. Let's try zooming in from 600 to 900. We will magnify and enhance. Okay, that's a little bit better to see. They are keeping the same period. My theta amplitude's going down. My phi amplitude definitely going up. I suppose that might be physical, because as the orbit is precessing around, you're going to get less variation in theta, more variation in phi. We'll definitely want to take a look at what's going on with our conservation of energy, just to make sure that this seems legit. Although I thought I got rid of my initial theta dot and phi dot there. Okay. The plot thickens. Why don't we try making a graph of the Cartesian coordinates? So let's try an x list equals r times, this one gets sine of theta times, sine theta times cosine of phi. And you're allowed to do this with a list because it's going to take each item in the list and put it through sine and cosine to create a list for x. Yeah, that worked. Then we'll do the same thing for y. Let's see, so I have an r. Now I want sine, everywhere a sine. And then I want z list equal to r times cosine of, this one just gets theta list. Good. So I have theta, phi is the one that changes there, and then I get theta here. Okay, so now how are we going to visualize this? Because if I want to create a plot, I can certainly do that, but I have to do two at a time. Oh, that's some cool stuff there. Wow. A wishbone thing or something. Let's try X list and Z list. Let's try within the bowl itself, like looking down on the bowl. This is what we see. Okay, so this looks fine from a conservation of energy perspective, just because it's going back and forth this way. And so the height's guaranteed to be okay because it's going to stay on the edge of the bowl. The only problem that might be here is if this is like it's creeping that way. There is also a way to do a 3D. Let me go find that. Right. All right, so I'm going to take an example here from the Matplotlib documentation. We're going to create a new figure with a 3D projection in it, and then we're going to do, what is this, ax.scatter. Then we're going to put in x list, y list, and z list. Although I might, let's see, z is the thing that's going vertical. Okay, so their z is my y, so I just need to flip my z and my y here. That's going to make the handedness wrong in terms of whether they're going clockwise or counterclockwise, but for our purposes, that doesn't really matter too much. Oh, yeah. This thing is actually upside down because we defined y needs a negative sign on here. Now you see why I put the negative on there to make it go downward into the bowl. Okay, yeah, that's about what we would expect. I think it's drifting a little bit because it shouldn't be moving along this axis. So we might be getting just a little bit of numerical error creep in there, but it's giving me the right idea there. Let's now try the whole thing again. Let's give it a little bit of speed in the phi direction this time. All right, we are done with the simulation. Let's run our graphs here. Oh, okay, this is where things get really, really interesting because this is where you start to see, the two variables, they're no longer just oscillating with a sine or cosine anymore. It's still a periodic, right? It's still got waves, but now it's some kind of summation or product of sines and cosines together. And they're no longer in phase, right? So like here you've got a maximum in theta while you've got a 0 in phi. Here you've got a minimum in phi while you've got a 0 in theta. And so this is where you get this kind of really interesting behavior here. Another way you could view this, of course, is with my favorite, the phase space plot. So let's make a phase space plot of theta list and phi list. PLT dot, do you have to spell it out? Oh, you do spell it figure, excuse me, plt.figure. Yeah, this is where it gets really interesting because this is now when you view theta versus phi, or phi versus theta, when you view orange versus blue, this is the thing you get, right? This is the stuff I live for, these pretty graphs here. They're showing you, what kind of trajectory it's tracing out in the coordinates that we've actually set up to matter. Here, let's try our Cartesian coordinates now. X versus Z, of course, also looking interesting. You can kind of see how this maps onto the X versus Z now because you're still graphing theta and phi. You're just graphing a different combination of them here. And so you're taking this graph and applying some trig functions to get this graph. And then, of course, here's our bowl pattern, which is pretty well like what we saw in VPython, right? So it's still moving along the edge of the bowl there.